Yes, so today in this particular video, what we are going to do is we are going to discuss about the Boolean algebra and how we are going to add, multiply, and subtract using those binary numbers that are the uh, main focus of this digital logic design is the binary numbers. We must understand each and everything related to those binary numbers. Although we have studied different type of number systems, but in the digital domain, we only works with the binary numbers, and then we must understand how we can add, subtract, multiply with those numbers, and how do we do the real algebra. So let's start this video. See the outline that these are the things that I'm going to cover in this particular video. So as you all guys must be knowing that George Boolean was a scientist who invented this Boolean algebra in the month of December in 1864. He was the professor of Queen's College, Cork, Ireland, and he was born and brought up in Ireland, and he did the same thing. He did his research in Ireland itself and published this research, the Boolean algebra. So, what are the basic Boolean equations? Is how do we going to use those Boolean equations in our calculations? So, as we know that we have AND gate, OR gate, NOT gate. Similarly, according to those logic gates only, we are having some Boolean functions. Suppose if there is any output Z that is having the inputs two inputs A and B, then the output of that particular Z will be multiplication of both of them. Similarly, if it is a three-input device, a three-input AND gate, then it is the multiplication of CD. If CD, E are the inputs, then if it is a four-input gate, then it must be having four inputs of F, G, H, K, and the output must be represented by any of the different variables. Similarly, if it is all gate, two-input all gate, then it will be showing the output as A plus B. And if it is three target, then it must be showing the A plus B plus C. And if it is a four gate input, then for input gate, then it must be showing out like this. Similarly, if it is a NOT gate, then it will just provide you the complemented function of the applied input. So if A is the applied input, then output of that particular NOT gate will be A1. Similarly, if you are having four input gates, then it must be showing the output in this particular fashion. So what is the two-level logic? For example, let's consider that example, this equation of Z of A, B, C, D, which is having the of AB plus CD. So this equation represent here the Z ABCD means that this output function of this function Z, it is having four variables, and those variables are defined inside the brackets. So ABCD are the four variables on which this function depends. And what is the correct output? Output is AB plus CD. Now, what this AB plus CD define actually? This AB plus CD defines. AB plus CD defines that AB and CD are the terms of expression. They are represented in the form of multiplication. Like it must be the output of AND gate. It is also must be the output of AND gate, and addition of both of them is being represented. So this is the sum of product form. And what is the sum of product? Some form we'll be explaining in subsequent classes. So this form of representation is called algebraic expression. So if any function is being represented to you in this particular manner, that in the form of equation, then it is called the Boolean algebraic expression. And for this function to be true, that means for this Z to be true, either A and B should be true or C and D should be true. What is the meaning of true? That A multiplication of AB should be high or multiplication of CD should be high. High means that it must be 1. Multiplication of AB must be 1 and multiplication of CD must be 1. Then only this output will be 1. So when we talk about true and false, that means if this function Z can be true only when Z is equal. And when can Z equals to 1? It can be possible that either if multiplication of both of them is 1 or multiplication of both of these C and D. So I guess now you have understood what is the Boolean algebraic expression, how it can be represented, and how it must be read. So this can also be represented in the form of truth table expression, just like we have the basic functions. We can also compress the truth table for any given function. In this part, what is the given function to you? The given function of AB plus CD. Right. So the given function was AB plus CD. So here we have A and B are the input. These two are the inputs for the function. And these two, C and D, are the other. So multiplication of both of them, if we pass them through an AND gate, then our output should be AB, and the output of this logic gate will be CD. And the resultant output Z equals to AB plus CD. So this can also be presented in the form of table. As we can see, we are having four variables like AB and CD, and the output is Z. So this is our output Z, and the inputs are ABC. So multiplication of both of them AB can be mentioned in this particular column, and multiplication of C and D can be mentioned in this particular column. So when you will multiply A and B, obviously output will be 0 here. When output will be 1 in these four cases, or multiplication of output A and B can be 1. Similarly, when your C and D both are 0, then only your output of C and D, CD will be 1. So we can consider that when is our output Z is 1. Output Z will be 1 only when A, B, and CD, any one of the A, B, and CD is 1. So here are the cases. This is the case 1, this is the case 2, this is the case 3. And these four cases we have here, we are having output of either AB or CD is 1. So we'll be getting the output here in all of these cases. 1, 2, 3, 4, 5, 6, 7. So in these 7 instances, our output of Z is, because either AB is 2, CD is 2. So there are some other example of Boolean expressions that you can encounter in your study. That these are the examples. The Boolean expression can be represented in either of the form. It can be represented like AB plus CD plus BD bar, or BD complement, or it can be represented as CD plus A bar B bar, or it can be represented like AB plus C. And if you are using a full adder case, in that full adder, what do we have? We have 3 inputs. So A, B, and C. So C is represented as C in. So output of that can be represented as AB plus AC plus BC. Similarly, if it is having a multiple input function, then your output can be represented like this as well. So even equations can be more complex to this. These are the few examples, and you can see like the examples we are having. Similarly, we can have more complex equations, and these equations must be minimized. They must be minimized to reduce the requirement of AND gates or logic gates. Whatever logic gates we are required to minimize the expression. If the equation is very complex, then obviously the number of required logic gate will be. So to reduce the requirement of gate, what we need to first minimize the function, then we can realize them using gates. What is this realization and how can we minimize? We'll be studying in subsequent lectures. So in this particular lecture, we'll be focusing on how we can reduce this expressions using real algebra. So these are the basic identities of real algebra. That how we have, what are the laws that we can implement or we can apply to reduce the Boolean expression of Boolean function. So let's consider the example from our gate. That means if there is any input x, if you are adding x with something, so result x plus 1 is 1, because it doesn't depend. It does not depend on the value of x, whether it is 0 or 1. Obviously, if 1 is high, then output will be high. That is the logic of our gate. So then we will study in the logic gate dimension. When we study about the logic gate, then we will be able to understand through those truth tables of each and individual logics. So if x is added with x, result will be x, because if it is 0, obviously it will be 0. So the output will be 0. If x is 1, obviously it will be 1 plus 1, and output will be 1. So whether your x is 0 or 1, your output will always be equal to x if you are adding x plus x. That means in the case of AND logic, if I multiply x with 1, obviously the result will be x. If x is 0, I will get 0 as 0. If x is 1, I will get 1 as 0. Similarly, if you multiply x with 0, whatever the value of x is, your output will be 0 because you are multiplying x with 0. Similarly, if you will multiply x with x, your output will be x for sure. So these are the 6 logics, expression identities that we have seen. There are multiple other identities also. This is x plus x bar. If x is 0, x bar, obviously x bar will be 1 because it will be complemented of that particular function. The result will be 1. Similarly, if x is 1, then complement will be 0, resultant will also be 0. So whatever be the value of x, x plus x bar, or a plus a bar, b plus b bar, c plus d bar, or whatever be the variable is, the complement with this function, addition of the complement with this function will always relate to 1. Similarly, the multiplication of complemented function will always be 0. And complement of complement is always a normal value. If a will be complemented twice, then the resultant will be a. So if you have a in the input and you are passing it two NOT gates, and you have applied two NOT gates in the series, so your output will also be a, will not be complemented out. If the complemented input you are providing and passing it with two logic gates, two NOT gates, then obviously your output will also be a bar, because it will be complemented twice. So if it is a bar and if it is a bar and you are passing it through the two NOT gates, then obviously you are a bar. Similarly, we have another real loss. One is competitive law. Here you can write x plus y plus x. You can just reverse the variables. It will not affect your output. Similarly, this is a competitive law. In the terms of addition or multiplication, it's x dot y, always equals to y dot x. Then we have associative law. Here, if it is ORing function, that means you can add x plus y. If y and z are in combination, then you can always write x plus y plus z. Similarly, in the multiplication function, you can always write x y z equals to x y multiplication. So no issue with here. You can either you can exchange the variable, the reverse order in the commutative law, and in the associative law, you can write it like this. The most popular one is distributive law and absorption that we must focus on. So this is the distributive law. That means if you are multiplying x with the y plus z, then you can always write x plus y z. Similarly, if it is x plus y z, then you can write x plus y multiplied with x plus z. Here and distribute over, and here or is being distributed. And so you can see when you or x with y z, and you can always write x plus y, and x resultant will always be x plus y z of y, because when you multiply x with x, so resultant will be x dot x. So x dot x means a dot b. X dot x means a dot a, and a dot a, x dot x will always be that I will go to here, and x dot x is always x. So this will be nullified, and you will left with x plus y z. Right. Then one of the law is absorption law, that you will understand that how it functions, how that behaves. In the absorption law, what we did is this distributive law, x plus y z, where you write something like this. For example, a plus, sorry, we write a plus ab, right? So when you write a plus ab or a plus a bar b, at that case, what happens? So absorption law is one of the type of distribution law. So how we can write a plus a bar b? We can write a plus a bar multiplied with a plus b. So a plus a bar becomes 1. And as it is being multiplied with a plus b, so 1 dot a dot b will always be a plus b. 1 dot a plus b will always be a plus b. So a bar will be nullified. So that's why it is called absorption. It is one of the type of distribution law only in order to study it separately. Then comes the de Morgan's law, the complement of any ORing function will always be the complement of individual terms, individual variable with the multiplication. And similarly, if it is an ending function, then the resultant will be x bar plus y. Right? And when you compare both of them, the result will always be same except the complemented function. Right? So these laws and theorems that we have studied so far, what should I say? These are the 17 laws that we have studied, starting from here. This was the first, second, third, fourth, fifth, sixth, and similarly we go to 7, 8, 9, and then 10, 11, 12, 13, 14, 15, and 16, 17. 17 laws will be useful for us to implement in the Boolean laws, Boolean algebra, where we are going to minimize any function. So suppose if this is the function given to you x bar y z plus x bar y z bar plus x z, and if you want to reduce this function, then how you can reduce? You can just take x bar y common because it is common in both of these terms. Then you can take x bar y common. Then what is left? Z plus z bar. So this is what the absorption law is. When you take x bar y common from the distributive law, with the help of distributive law, this z plus z bar becomes 1, right? So you just nullified the z from these two midterms. So you have absorbed the z. That's why it's called absorption. So what is left is left with x bar y plus xz. So this is the final solution. You cannot nullify it furthermore. So this is the final solution that you can get. Similarly, you can also reduce other function as well. And you can also implement by using logic gates. If the function is given to you x bar yz plus x bar yz bar plus xz, that is the same function that we have discussed. So you can see there are 1, 2, 3, 4, 5, 6. 6 gates are required to implement this function. Now, after reducing it to x bar y plus xz, only 4 gates are required. So then you can see that we have revised the here 6 gates required, and now we are able to implement this by using only 4 gates. You can see the benefit of this minimized Boolean algebra, that how we can reduce the requirement of gate by applying Boolean logic gates, Boolean laws. So there are few other examples that you can use. Suppose if it is a function given to you x plus x by what you can multiply x with 1. So answer will always be x. And if you can take x common from this by applying second real law, then you can take the x common from the distribution law. 1 plus y will be 1. So x dot 1 will be x. This is the output you can get after applying few billion laws. 3 billion laws. Similarly, if it is the function, then what you can do, you can take x common, then y plus y1 will be, then x dot 1 will be 1. And if it is x plus x by, then you can apply the distribution law. It's x plus x bar and x plus y. This was the example I was talking about when I was explaining the absorption law. So x plus y x bar becomes 1. So what is the result? The result is x plus 1. So you can see that you can reduce the number of logic gates requirement, and you can also reduce the function to a extent level, to a minimized level. There are other examples as well from the text that you can see. Here we have x dot x plus y, that you can apply the x distribution law and you can get the result at x. But here you can see that if I try to simplify these equations by 2 methods, so there are methods that you can use. Either you can use this one, you can use 14 for distribution law first, and you can rest of the things again. If it is given to you like this, x plus bar dot x plus bar, then what you need to do, you can multiply first, and then you can take few things common. This y dot y bar becomes 0, and x dot x bar becomes x, and then you can take x common here, and you can solve it, so that the result will be x. So these things can be done if few changes are there in the given expression, then you need to apply different distribution law, different laws to solve that function. These all like same to you, that x plus x multiplied with x plus y, or x plus y multiplied with x plus y, or x multiplied with x plus. They might look similar to you, but they are different. And for each and every different expression, you need to apply different laws to solve. Apart from these Boolean laws, we have other methods as well to reduce this function. The most popular one is Carnot and K-map. We'll look into it also. It is very easy to use, and you can get the minimized function as well. And you must always remember that if you are reducing a complex function, then there must be multiple solutions for that. Because each and every individual can apply different Boolean laws according to his own thinking ability. He can apply whatever Boolean law he wants. But resultant should be minimized function. So it might be the possibility that you are getting a different answer and your friend is getting a different answer. Then you must not be worried about it, because in Boolean law, you individual person can get different answer, but they must be having the minimized function. But when we solve K-map, in that also the minimized function you will get. Here you need not to worry. Very simple. So let's complete this video here. In the next subsequent video that I will upload in that particular thing, we'll be discussing about the binary addition and what are the devices that we use for addition. Then we'll study binary subtraction, then what are the devices that we use for, and then parallel adders and subtraction. We'll see digital devices, those parallel adders and subtraction devices are there. Then we'll do the multiplication, and then we'll see what are the complements and how do we subtract using complement. In normal decimal subtraction, what we did, we just subtract the numbers from each other. But in Boolean in digital devices, if you use the number of required logic gates, then you can use adders. That means AND gate only or gate only to the subtraction. You need not to use any different logic gate for that. So we'll see in the next video. So this is all for this particular. Next, we'll study these things in next.